Okay, I guess we can get started then. Welcome everyone. I hope everyone's here for the ESWEEK education class, Memory-Centric Computing. We're going to cover a lot of interesting topics and cutting-edge topics in how computation is done in a more data-centric or memory-centric manner. And I should warn you that this is going to be relatively fast-paced. If you have questions, feel free to ask. I don't know what the format is exactly, but I can lecture about this for hours and hours, and I have a lot of slides on the topic. So feel free to ask any questions whenever to interrupt me. And clearly, this topic has a lot more material than we can fit into 2 hours. I'll try to give you a summary of it and also the mindset of memory-centric computing, if you will, because it requires a mindset change to enable more memory-centric programs, memory-centric architectures, and memory-centric thinking of computing systems, even from the computing theory to begin with. And I'll point you to some resources as well. Let's get started, I think. Okay, I guess people know me. I'm a professor at ETH Zurich. I'm going to cover some introductions at the beginning, introduction to my group as well. I'm interested in building fundamentally better architectures. We focus on computer architecture, hardware, software, co-design, computing systems, bioinformatics, and hardware security. And you will see aspects of all of these in this talk, hopefully. And these are 4 key directions that we are pursuing. And again, you will see aspects of all of these in this talk. I think going forward, computing platforms need to become fundamentally secure, reliable, safe. This is critical. We need to become fundamentally energy efficient, memory-centric, which is really the topic of this lecture. But I will touch upon the other topics as well. We need to become fundamentally low latency and predictable in our architectures. And going forward, to achieve the highest energy efficiency and performance, we should specialize our architectures to the workload that's important for the system that's being designed for. Okay, I think this brings us to the transformation hierarchy of computing. You need to solve problems in computing. And computer architecture normally sits between the interface between the hardware and software, as well as a microarchitecture. But I will take a much broader approach to computer architecture in this talk. It's more like all the way from algorithms to devices. It's an expanded view. And I think going forward, to achieve the highest energy efficiency and performance, we must take that expanded view. It's already happening, but it's going to happen even more going into the future. And we should co-design across the hierarchy from algorithms to devices and specialize as much as possible to achieve the goals of the computing system that we want to design. These are, I'm not going to spend a lot of time on the slide, but these are some of the research topics that are going on in my group that we will touch on. But I'm interested in broad research spanning applications, systems, logic, with architecture at the center of it. And this is my research group. A lot of the research that I'm going to talk about is done by these folks. So I acknowledge them at this point. And if you're interested, you can read some of our newsletters. And if you're interested, you can also watch some of the videos that we put out. And I will briefly mention the mindset so that hopefully you get an idea. I strongly believe that teaching and research are coupled. They're 2 sides of the same coin. Research enables new insight, new ideas, and you teach them later on, and they become old insight. And basically, it's a cycle that keeps growing. And both of these have to happen so that progress happens going into the future. And I'm going to talk about a lot of ideas, and I encourage people to focus on insight and new ideas, as opposed to maybe getting too much bogged down on the implementation details, at least for this talk. Of course, when you write a paper, get bogged down on the implementation details and make sure that things work. But I'm going to stay not so implementation oriented in this talk, let's say. And we focus a lot on learning and scholarship, and I think I'd recommend everyone to do that. And with good mindset, good goals, and good focus, hopefully people who are taking this class and can make a good impact on the world. I would also recommend, I'm going to talk about a lot of things, but we release a lot of videos on our YouTube channel, and certainly the computer architecture courses, digital design courses are released, and many other talks are released. I would recommend you take a look at them. If you feel like, for example, you're missing some background on some topic, this is a freshman level course on digital design and computer architecture. And this is the more advanced computer architecture course. And currently the computer architecture course is happening, and we're live streaming on YouTube. So anyone is welcome to attend and ask questions on YouTube. We also have seminar courses that go more in depth into papers, and that's also being live streamed. on YouTube. So feel free to attend that as well if you feel that these topics are interesting to you. We also have more hands-on projects and seminar courses that you can find online. We are also doing some live seminars. If you're interested in attending, feel free. There's one coming up in October 27th, which is very much related to the topic of this lecture. I'm going to mention this work, but it's going to talk about data-centric and data-aware frameworks for essentially fundamentally efficient data handling. This is one of my PhD students who did her PhD thesis on this topic, and she's going to deliver this lecture. Okay, I also believe in open source artifacts quite a bit. We release a lot of open source tools, and what I'm going to talk about, a lot of it is released open source. And if you're interested in doing research, for example, on memory-centric computing, you can get started on it relatively easily with the open source tools that I'm going to mention. For example, the PRIM benchmarks are the first processing in memory benchmarks that you can run and analyze in existing processing in memory systems like UpMem system. Damu is another benchmark suite. Remulator is our DRAM simulator, but you can find many, many other things in our GitHub. Okay, and you can find a lot of talks, as I mentioned, and I'm going to just flash these and move on, let's say. And I would recommend people to think about maybe watch this talk, which talks about doing impactful research, where I outline a bunch of principles that I like following, for example, in my research to reach as high impact as possible, let's say. And separately, I also highly recommend this reading by Richard Hamming. I'm assuming many people who are attending this course are interested in doing research or doing something important, let's say, that can change the world in computing. And I like the seminar that Richard Hamming gave about, I guess, 25 years ago now. Well, I guess it's 35 years ago now, right? Yeah, 35 years ago now, where he outlined his philosophy on how to do research. And I'd recommend looking at that. And this is kind of a summary of what he discusses at the end. Basically, know yourself, your weaknesses, your strengths, and your bad faults. How can you convert a fault into an asset? The successful scientist changed the viewpoint, and what was defect became an asset. So what may seem like a defect to you in anything, you can turn it into an asset by looking at it with a different mindset, let's say. And I'm not going to read all of these paragraphs, and there's a lot more, let's say, words of wisdom by Richard Hamming, who invented the Hamming codes as well as error correcting codes, and essentially a coding theory, let's say, in this particular talk. He also has a series of lectures that you can find online. I forgot to put them over here, but he delivered these lecture series in Naval Postgraduate School in 1995. And he really talks about how to do research and how to have a high impact on the world with that research. I'd recommend looking at it. Okay, I guess with that backdrop, let's start the main subject of the course. It's memory-centric computing systems. Well, it's called memory-centric computing, but I added systems over here. Clearly, we want to build systems based on memory-centric computing principles. And the problem is that computing is bottlenecked by data, especially today. Data is really key for all important workloads, machine learning, AI, genomics, whatever you can think of. I'm going to give you examples. These workloads require rapid and efficient processing of large amounts of data, and data is increasing. We can generate more data than we can process today. So if you look at some, let's say, more traditional workloads, they're having difficulty scaling and being energy efficient because there's a lot of data that we're dealing with today. As a result, data is a performance energy bottleneck. If you look at more mobile workloads that everybody uses today, in fact, in our call, we're probably using all of these workloads that you can see on your screen. Well, at least different versions of it, let's say. And data becomes a performance energy bottleneck in those workloads as well. And we do a lot of work on genomics, genome analysis, and this is, I believe, an emerging area that's going to be a lot more important into the future because it has enormous implications on medicine, health, and also pandemics, as we are seeing currently. But today, we can generate a lot more genomic data than we can process because the cost of genome sequencing devices has reduced dramatically, much faster than a transistor cost has reduced over decades, as you can see over here. As a result, we can generate much more genomic data than we can process because the computation that we do on this data is also expensive. I will talk briefly about this, but basically today sequencing machines are extremely good. They're high bandwidth, relatively reasonably low latency. They can be better, of course, but scientific discovery and medical advances and let's say disease understanding is really bottlenecked by how fast we can really analyze genomes, how fast we can really compare them to different things, how fast we can really build an understanding of, for example, different treatment procedures based on different genomes. So personalizing medicine has become difficult because even though we have a lot of data, we don't know how to analyze it fast and efficiently. For example, if we have a device that we can give to the doctor and the doctor quickly makes a personalized decision as to which drug would fit better, that would be very nice. But that decision may take days or even weeks today, depending on the analysis that you may want to do. So our goal is really to reduce that time, but we're bottlenecked by the performance and energy bottlenecks of data. And this is an example. This is basically becoming real. This is an example device that can actually sequence a genome relatively quickly, and you can see that relatively cheaply. But there are a lot of bottlenecks in the current tools because of the data again. Again, I'm going to refer you to these papers. I'm not going to go into details of this, but processing near memory, processing inside memory, memory-centric computing can actually accelerate workloads like genome analysis. And we actually have some works in this area. And if you're interested, this is a relatively easy to read high-level overview paper that talks about accelerating genome analysis and talks about different flavors of how you can accelerate genome analysis, including FPGAs, GPUs, as well as memory-centric computing. Okay, there's also specialized hardware accelerators that you can design, hardware software co-designs that you can design to accelerate approximate string matching, which is at the core of many genomic analysis, as well as other text analysis. And if you're interested, I'd recommend taking a look at this paper, for example, and that might inspire you to do other accelerators. And I believe we have a lot of need for accelerators going into the future in this domain, because the future is actually very embedded, as you can see. You can see that this is a genome sequencing device that was actually already available a few years ago, and you can plug into your phone, and you can also do a genome sequencing over here. But again, we're bottlenecked by the data, and we're actually trying to push the computation into the device, into where the data is collected, so that we can minimize the data movement and minimize the amount of computation that becomes needed, the amount of storage that becomes needed later on also. And again, I would recommend these works if you're interested in this direction further. And there we have detailed lectures on genome analysis. If you're interested, you can watch them online on the channel that I mentioned earlier, but you can also find these slides. I will put these slides online, and I will also send it to the organizers if they're going to put them online. But you can find this information online by looking at the slides. Okay, this was an example embedded application. I believe actually genome analysis has to be done in massive scale in data centers, as well as in personal private scale, let's say, and also in the hands of a doctor. So it has to be very, very embedded as well. So this is an application that's really spanning all types of computing systems. And I use this example to show that data really overwhelms modern machines. Even though I didn't give you some numbers to you can easily find the numbers in the papers, basically. Basically, data overwhelms modern machines today. It overwhelms the storage and memory capability, computation capability, communication capability, as a result, computation capability as well. It greatly impacts robustness, energy, performance, and cost too. So if you look at a computing system, fundamentally, it consists of three key components: computation, communication, storage, and memory. And if you look at the history of computing, a huge amount of effort is really spent on optimizing the computing units. Today, we are actually very good at doing that. We know how to build extremely high performance and reasonably energy efficient high performance processors, very good accelerators, very good GPUs, etc. But we have not optimized as much the communication and memory and storage units. And this talk is really about that, basically. Even though these units are not optimized as much, they're the bottleneck today. And in fact, they're occupying most of our system area and system cost. And this picture, this cartoonish picture, kind of quantifies that, basically. So this is my cartoonish picture of a multi-core system. It's an old picture, but I think it still remains. In fact, things are getting worse. Even bigger chunks of a machine is becoming occupied by caches, interconnects, other caches, other interconnects, etc. But the point in this picture is that you have processing elements. Let's call them cores. They could be accelerators also. It doesn't matter. Some computation elements, let's say. They're a small part of the system. The rest is caches, interconnect, other caches, other interconnect, memory controllers, other interconnect, other caches like main memory, other interconnect, and storage. So most of the system is really dedicated to storing and moving data today. And even then, memory and storage is a huge bottleneck in our systems, as I will show you later on in this talk, quantitatively as well. I'll give you one example soon, basically. In these workloads, for example, we studied these workloads together with Google a few years ago, and we have a detailed analysis of it, arguing for memory-centric, more near data processing in these workloads. based on the observation that more than 60% of the total system energy in a small mobile system is spent on data movement in these workloads with cutting edge input sets. Okay, you may want to take a look at this paper. We're going to get back to it toward later parts of this lecture, of this class, so that you can have a better understanding of this number, perhaps. Okay, my axiom, based on everything I said so far, is that if you want to build intelligent architectures going into the future, and I believe we do want to have intelligent architectures, we need to handle data well. So, of course, this brings the question now, how do we handle data well? And I think there's a three-pronged approach for this. First, we need to ensure that data does not overwhelm the components. We're designing some components, hardware components, as well as software components. We should ensure that the data doesn't overwhelm them. How do we do that? I think we need to design intelligent algorithms that minimize data and minimize data movement. We need to design intelligent architectures that achieve the same. And more importantly, we need to design whole systems, algorithms, architectures, devices that can do essentially this, that can avoid overwhelming itself. Okay, so that's one direction, and we're going to focus a lot on this direction in this talk. But there are two other directions that are also important and interesting, and we should explore, and they're synergistic with the first one, in my opinion. We need to design the system because a lot of data and metadata is flowing through the system today, and the systems in their hardware decisions or the software decisions are not really taking advantage of this vast amount of information that's flowing through it. Basically, we can learn from the data that we process and learn from our architectural and system level decisions in the hardware by incorporating machine learning based policies inside the hardware as the software. I'm going to give you an example maybe in the next slide, but that's the idea over here. And the third is we want to understand and exploit different properties of different data so that we can make better decisions on data. For example, if at the semantic level, we can understand the compressibility properties, security properties, error tolerance properties, locality properties of data, we can design memory systems that can treat different data differently. And as a result, we can scale the memory system better. We can make the memory system more efficient. We can make the memory system more higher performance for data that needs it and lower performance or lower energy for data that doesn't need the performance, right? So we can improve our algorithms architectures in various metrics if we can actually understand and exploit the properties of data. So I believe these three directions are actually quite important and synergistic. So let's take a look at how architectures deal with these three directions, let's say. Today's architectures, as I said, are very processor-centric as opposed to data-centric. As a result, they move data a lot. And as a result, they're not good at dealing with data. And we're going to focus a lot on this direction in this particular lecture. The second direction is today architectures really are not good at learning from the decisions they make on data. So, for example, if you look at a memory controller, my cell phone is, let's say, 6 years old. It's still executing exactly the same algorithm that a human dictated it to execute when the human designed it, based on limited information and limited capability the human has. But there's been a lot of workloads that have executed on this mobile device. And I have actually interacted with this mobile device many times. And the memory controller never learned anything from that interactions and from those workloads. Basically, it does not make data-driven decisions. The learning capability is essentially zero. I think we should change that, basically. We should really, if you want an intelligent architecture, that intelligent architecture should really learn from its past decisions. It needs to be data-driven. It needs to make better and better decisions over time, optimize the system to the user, to the workloads, to the operating conditions, and as a result, become better over time. Right now, it's becoming worse over time because it's making the same decisions, even though the workloads are becoming more intensive and users are becoming more intensive or more, let's say, less patient, etc., more demanding, right? Okay, I'm not going to talk a lot about this direction, but I think it's important. Some examples of this is some of the work that we have been doing in using reinforcement learning to improve memory control decisions and using reinforcement learning to improve prefetching decisions. That's going to appear at Micro actually next week. If you're interested in attending Micro after ESWEEK, you can also attend Micro and see what is there. Okay, and the third dimension is really today's architectures are usually, especially the general purpose ones, but even the special purpose ones for the most part, they're treating data, all data as the same. They don't have enough information, enough semantic information about the properties of different data. As I mentioned, compressibility, locality, privacy, security, approximability, error tolerance, etc. You can come up with many dimensions of the properties of data. And this information doesn't get extracted and definitely doesn't get communicated to the underlying hardware and also usually the system. As a result, systems make component-aware decisions as opposed to data property-aware decisions. For example, again, I will pick the memory controller. The memory controller makes decisions based on the structural organization of DRAM. Do you have banks? Do you have rows? Do you have channels, etc.? And whatever happens to be in its queue, as opposed to criticality of the data that it's trying to access, that the processor is trying to access. And this is one example. Okay, again, I'm not going to talk about the data-aware architectures, but again, this is a very important direction, in my opinion, to explore going into the future. And these three directions are actually synergistic: data-centric, data-driven, data-aware. They're really synergistic with each other. And if we have time, we can talk about that synergy, but we may have to leave that for some other lecture. Okay, so as I said, I'm going to focus especially on data-centric architectures, memory-centric architectures, but keep also these data-driven and data-aware aspects in mind, because I believe they're also part of being memory-centric. Okay, so this is, let's say, the goal to design fundamentally better architectures. How do we make them data-centric, data-driven, and data-aware? In my opinion, again, we need to revisit the entire stack to enable. We have to take an approach that's hardware-software cooperative, designing all the way from algorithms to devices and co-designing them as well. But I believe, even though this may seem like a daunting task, we can get there step by step. And hopefully I will show you small or relatively small changes you can do to enable this mindset that can be more data-centric and data-driven and data-aware. Okay, so let's jump into data-centric or memory-centric architectures, which is the first direction. And if you step back and think about what should the properties of a data-centric architecture be, I would come up with this list. Actually, I came up with this list. Maybe you can add to this list. But I will argue that you should have at least 4 properties. First, this architecture should process data where it resides. Basically, you should have the capability of doing operations on data wherever the data resides. Storage, main memory, caches, processing units. Clearly, we are able to do that today. But we should enable processing capability in all of the memory structures that we have in the system, because it may make sense to do the processing there, as opposed to moving the data all the time, only to the processor or the accelerator. Today, we have no choice. We need to have that choice if you want to be data-centric. Okay, second, since data is important, we need to have low latency and low energy data access. We need to have low-cost data storage and processing. And there are a lot of ideas over here that I'm not going to talk about since we don't have time. And we need to have mechanisms for intelligent data management. We need to have intelligent controllers handling robustness, security, and cost. This is where also data-driven architectures that are self-optimizing come in as well. So I'm going to mention this intelligent data management a little bit to motivate processing data where it resides as well. Okay, so let's jump into processing data where it resides. I also call processing data where it makes sense. You can call it memory-centric or data-centric computing as well. But I think we should be able to have the capability to process data, if it makes sense, in anywhere essentially, while the data is flowing through the network, also in the router, potentially in the certainly in the memory, in the storage, etc. And this is not a new idea. Clearly, this idea has been around for a long time. It's called processing in memory. We're going to distinguish between processing using memory and processing near memory later on. But the general idea is old, basically. And this is a paper from more than 50 years ago, 52 years ago, that was published in IEEE Transaction in Computers. And this is another paper by Harold Stone that argues essentially for the same thing from a different perspective. Okay, so people have argued these ideas, and they have not clearly happened in the course of the last 50 years. Why do we expect them to happen today? So why is it interesting again today? So I will argue that we're today in a very special situation. Basically, if you think of the computing stack, you have the technology at the bottom and applications and algorithms at the top. Both of them are squeezing us, basically. Technology is squeezing us to do something different in memory. Applications and systems are squeezing us to do something different, because they're both bottlenecked by some things, basically data in particular, but also other things that the technology is bottlenecked with. So let's look at the technology scaling aspect. Basically, today we have a huge push from technology to do something different with our memory systems. Basically, DRAM, the main memory technology that we design our systems with, is not scaling very well. It's actually getting closer to the end of its technology scaling. We are having a lot of difficulties. I'm going to mention some examples of this without going into a whole lot of detail, because I want to use that as a reason for studying memory computation as opposed to going into detail in that topic. But basically, today, industry is very much open to new memory architectures. They're examining controllers close to DRAM. They're examining new ideas, which was not the case 10 years ago, for example. But today, there's a huge push from technology to do something different. So example ideas look like this. Some of these are examined in the past. More recently, the UpMem company actually put processing units inside the DRAM chips. And even more recently, Samsung actually did essentially the same thing, more specialized processing units inside the DRAM chips. These are going to be similar to the ideas that I'm going to describe that have been around for much longer than these chips, basically. So basically, it is happening today because of technology scaling. Well, that's one of the dimensions as we discussed. And technology scaling issues have been around for some time. This is a paper that I was invited to deliver at the International Memory Workshop in 2013. If you're interested in that perspective, at that time, this paper kind of talks about a lot of the technology scaling issues that we're going to have with main memory and DRAM, and basically argues that we should be doing more memory-centric computation as well as other things that I'm not going to talk about here. But basically, it argues that memory scaling is going to become much more difficult. And as a result, we're going to have a lot of reliability, resiliency, security issues, and scaling issues. So we should really push more intelligence to the memory system so that the memory system can handle these issues on its own better. And also, we should put computation capable to the memory system because memory system is also not scaling from the data movement perspective. Basically, we're moving a lot of data, and also energy is being wasted a lot. So let me give you the reliability perspective first, because this is really at the heart of technology scaling. Basically, as memory scales, meaning as the technology node size reduces, we can pack more memory cells in a given area, right? And these memory cells bring us higher capacity. But unfortunately, it comes at a cost. And the cost is really reliability. So we did this study together with Facebook a number of years ago, where we analyzed all of the errors that they see in their data center that are related to memory. And we found out that there's a strong correlation between the density of the DRAM chip that's used in the server and the failure rate of the server. And you can see that it's a very strong correlation. As the density increases, server's failure rate increases because you get more memory errors. You get more memory errors because these chips are more vulnerable to noise because cells are smaller, technology scaled, cells are smaller, cells are more vulnerable to noise. There are more cells in a given area. As a result, capacitors are not only leakier, but also more vulnerable to noise. And as a result, you get the system level effect where errors are percolating up in the system and sometimes actually causing servers to lock down, let's say. Okay, I'm not going to go more into details, but this is some strong evidence as to how technology scaling affects itself in real production data centers. And if you're interested in a lot more data, we have actually published it in this DSN 2015 paper. Okay, so later we also built a lot of infrastructure to understand these technology scaling issues and DRAM in particular, because since DRAM is a major memory technology and it's not going to go away anytime soon, let's say, we should really understand it and enable it to scale, let's say. And I strongly believe that even though there are a lot of other technologies that are being examined today and they should be examined, DRAM is still very hard to dislodge, very interestingly, right? And I think if DRAM manufacturers end up actually using DRAM for other purposes, like processing, it will also enable other opportunities for other technologies as well, not just for DRAM. Okay, but basically we studied DRAM using FPGA-based infrastructures, which can test DRAM essentially rigorously with our own memory controller that's handwritten, let's say. And we actually have many versions of this infrastructure today. This is one version of the infrastructure, and we released the source code of this infrastructure online. So if you want to do experiments on real DRAM chips, you can get your FPGA and you can use our code, which is easy to program, I will argue, because it has a C++ API to do memory testing. And other people have used that. I'm going to mention at least one paper that have actually done it and that have found really interesting results, let's say. So this is the open source repository if you're interested. So while we were doing a lot of experiments in DRAM, we found out that DRAM is vulnerable to disturbance errors. Basically, you can predictably induce errors in most DRAM memory chips by disturbing the cells that you're accessing. Okay, that's the idea basically. So this is called the RowHammer vulnerability right now. It's the fact that you can induce predictably bit flips in commodity DRAM chips in a large number of DRAM chips. And this is really the first example of how a simple hardware failure mechanism, read disturbance in particular, can create a widespread system security vulnerability. And you can actually read some overview articles that are like popular articles that they forget software. Now hackers are exploiting physics. And I like this because this actually gets to the core of the RowHammer. RowHammer is all about fundamental physics of the DRAM device and electromagnetic interactions between the cells. And basically, by exploiting the fact that you can induce bit flips due to the fact that those electromagnetic interactions lead to the vulnerability, you can actually take over an entire system. Now, before we go into that, I'm not going to go into exactly how you do it, of course, since it takes a lot of effort, but I'll give you some references. What is the problem, basically? If you have not heard about RowHammer, memory consists of rows. And if you want to access one row, let's say one cell in a row, you need to apply high voltage to that row, to that word line. This is called activate in DRAM. And if you want to access some other row, you need to apply low voltage so that you can close this row first. This is called pre-charge in DRAM. Now, clearly, there's some electromagnetic interaction that will happen if you do high voltage and low voltage due to the coupling between different wires and the cells. And basically, we found out that if you keep doing this repeatedly, activate, pre-charge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, enough times before the memory cells get refreshed, it turns out in adjacent rows, you see bit flips. Some ones become zeros, some zeros become ones in vulnerable cells, depending on how the data is encoded. I'm not going to go into the details of it clearly. Clearly, there's a lot of interesting detail to explore and understand here, but it happens. That's what matters from a security perspective. And we call this the hammered row, aggressor row. We call this these the victim rows. And we found out that in most DRAM chips you can buy today, this is possible, more than 80%. Why is this happening? Well, it's because there's electromagnetic interaction between the word lines and the cells. As a result, electromagnetic coupling, I should say. As a result, when you keep doing this repeatedly, some cells that are vulnerable leak charge little by little at every activate, and eventually they are depleted of charge, and as a result, they lose their value, right? That was written before. And there are a lot of other interesting mechanisms that play into it that are explored in our papers that I'm going to mention later on, and also other papers, more device-level papers, but that's the gist of it. Due to the lack of enough electrical isolation, what you do in this row affects some other row that it should not affect. Clearly, it should not affect because you're not even touching that row, right? You're not even writing anything to memory. You're not even writing anything to the hammered row. This could happen just by activating and pre-charging. Okay, and clearly this happened. This is an industry-wide problem. And this is also a technology scaling problem because in older chips that we tested, we did not see this problem. The first appearance is in 2010, and all of the chips that we tested that were manufactured between 2012 and 13 are actually vulnerable to this problem. And I'm going to show you the results from later as well. But basically, in old chips, you couldn't do enough activates to cause this disturbance before the cells get refreshed. But in later chips, because cells became smaller, as well as cells became closer to each other, they became more vulnerable to this sort of read disturbance noise. And as a result, you could do enough activates within a refresh interval so that you can flip some values in DRAM. I will show you the number of activates, and it's going to be surprising, hopefully, well, if you haven't followed the research. So basically, when we wrote the paper about RowHammer, we said that the first sentence was, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I strongly believe this still. We need to have memory isolation to prevent such problems. And we said that someone can hijack your computer by taking advantage of these predictable bit flips. And that's essentially what these folks from Google Project Zero did. I would recommend you take a look at their blog post as well as Black Hat presentation. They have a beautiful security attack that basically takes over the system by taking advantage of these bit flips. I'm not going to go into the details of it. I'll refer you to some other papers that have also done something similar, but in a more sophisticated fashion later on. These folks, for example, showed that you can gain unrestricted access to systems of website visitors. These folks show that you can gain control of a smartphone completely deterministically. Again, I don't have time to talk about details. And there are a bunch of other works. I'm going to skip them. But more recently, these folks show that you can actually destroy the accuracy of deep neural networks, which are otherwise quite accurate. This is another paper that shows that you have a neural network that's quite accurate. But if you actually have a targeted RowHammer attack, you can easily destroy the accuracy of the network, inference accuracy, to 10%. Basically, your neural network, your, let's say, machine learning intelligence becomes useless. In fact, could become terrible for your safety and security if this is making decisions for you in self-driving, for example, or other safety, right? By basically making wrong decisions. So I think this is a serious security problem, safety problem, and also reliability problem across all of our computing systems, not only general purpose systems, but also accelerators that may potentially be targeted targeted with this type of attacks that are relatively easy to do, I will say. Corruption attacks are relatively easy to do. Taking over the system requires a lot more effort, of course, right? But here, to destroy the accuracy of a neural network, you don't need to take over the system. You just need to bit flip cause bit flips in enough weights in the system as these folks show. Okay, so this is the paper that introduced RowHammer, and that show that memory scaling issues are actually real, let's say. Even though there are other works that show that these are real, this is perhaps the one that gets exposed to the user as more than others, let's say. Okay, and if you're interested in RowHammer, we have written a retrospective paper that was published in TCAD last year. But this doesn't contain up-to-date information, even though it's a very good overview paper. I would recommend you to read it. A lot has happened more recently in RowHammer that I'm going to discuss. But how do we prevent the problem? I'm not going to talk about the RowHammer solution, but if you have an intelligent controller, if you design the controller to be intelligent, it can detect these RowHammer attacks and it can take action, basically. And that's the idea, basically. You need intelligent controllers to overcome such scaling problems. And RowHammer is one where an intelligent controller can be very effective. I'm going to mention one solution later on, but our initial paper also argued for intelligent controllers and system DRAM co-design to get rid of these RowHammer bit flips. Okay, what happened in 2020 is actually, it shows that RowHammer did not go away. It became even worse, basically. This is one paper where we analyzed more than 1,500 chips, DRAM chips, and basically we showed that newer DRAM chips are much more vulnerable to RowHammer. You can induce these bit flips only after 4,800 hammers, double-sided in 2 aggressor rows. And basically, the problem is getting worse because you can induce bit flips in more rows and also farther away from the victim row as well. And existing mitigation mechanisms are not effective. So we need to actually search for new mitigation mechanisms. Okay, there's another work that has happened in 2020 that basically showed that the solutions that DRAM manufacturers put into their chips to solve RowHammer, that they claim to be RowHammer free. So DRAM manufacturers proudly claim that, oh, we have some solution in our chips. We're not going to tell you what it is, but our chips are RowHammer free, period. End of discussion. And a lot of people believe that. But in this work, we showed that that's not true. Basically, you can reverse engineer those solutions just enough so that you can actually circumvent those solutions and actually induce RowHammer bit flips. As a result, the solutions that are claimed to be secure are not secure. I'm not going to go into details of it, but you can find lectures that I'm going to point you to later on this topic. But I find this fascinating, basically. And this is also a good lesson in security because it shows that security by obscurity is not a good idea. You should never underestimate, let's say, the creativity and cleverness of an attacker. Okay, and there are other works that show that it's very difficult to prove a DRAM chip, qualify a DRAM chip to be RowHammer free. There's a lot of testing that needs to be done, but still it's very difficult to prove. And I think these are really interesting works. And we also have some solutions in 2021 that basically have an intelligent controller that using Bloom filters identifies which rows are rapidly being accessed and throttles accesses to them with some hardware cost, of course, but intelligence always comes with cost. We human beings are intelligent, right? But we have some cost, right? Even our brains require some training. Our brains are not, let's say, cheap from, let's say, a design perspective. So certainly intelligence comes at a cost, and we need to pay that cost. And I'm not going to talk about these, but RowHammer is, let's say, alive and well, but we need to solve that problem. And there are 2 upcoming RowHammer papers that are going to be presented by my group at Micro next week that talks about the details of RowHammer, and also that basically shows that there's a methodology you can develop to actually circumvent all of the in-DRAM RowHammer protection mechanisms that the DRAM manufacturers that have put in to the chips today. If you're interested, you can attend these talks. But basically, the takeaway is RowHammer, a key technology scaling issue, is still an open problem, and security by obscurity is not a good solution. And we need more intelligent memory controllers to solve the problem. And if you're interested in this more, as I suggested, you can read the papers, and also you can watch some more specialized talks, let's say. So I think RowHammer is an example technology scaling issue that shows that we should be building much more intelligence into our controllers. Basically, we should be much more memory-centric. When I say memory-centric, it's really about the intelligence that we put into the memory system, right? Today, we don't put much intelligence. We cannot operate on data. We cannot even fix problems like RowHammer. Why not have some more intelligence over there so that the memory system can actually fix these problems and we don't have to deal with them? Okay, maybe a little bit more about this importance of the safety and security issues in memory, with the RowHammer being a specific example, but I believe there are other examples that are going to pop up if we don't actually take these technology scaling issues seriously and become memory-centric in handling them. So this is the Tacoma Narrows Bridge. It doesn't exist because a bit flip happened on it in 1940, and it crashed. It caused a safety, security, reliability problem. And it was lucky because there was no fatality over here, but other bridges were not as lucky. This is Seoul in 1994. This is Minneapolis. This is Genoa. And these bridges are critical infrastructure that humanity has designed. And they clearly pose safety, security, reliability problems when bit flips like this happen on bridges, right? I will argue that today's computing systems that we're designing across the board, embedded systems, data center systems, they're all critical infrastructure that we are going to rely on. Automotive systems, which most of which is embedded, as you know, they're going to make decisions for us. They're already making decisions for us. And if bit flips happen, we're going to see much worse consequences than these bridge failures, as I mentioned. So basically, we need to take these bit flips and technology scaling issues very seriously, and we need to think of security as preventing unforeseen consequences. For example, in a self-driving car, you have a lot of embedded systems, embedded logic, right, in there, controllers in there. Can you trust those controllers so that you can drive the car like this, like Mr. Bean, without even touching anything, let's say? If you watch this episode, you will see that he's touching. He's basically cheating a little bit, but I want a self-driving car where I can trust fully, right? But with these technology scaling issues not solved, I don't believe that we can trust a self-driving car fully. That's why we need to take it serious. So I think we have a huge challenge. We need to design fundamentally secure, reliable, and safe computing architectures. We need to predict and prevent such safety and security issues. And to be able to do that, we really need intelligence on the memory side, on the data side. In fact, we need to have intelligence across the computing system. We cannot afford not having intelligence on the memory side and let memory basically get corrupted due to these errors. And I think we're a little bit luckier than bridges, let's say. Bridges are hard infrastructure, whereas computing is more or less soft infrastructure. Even the hardware is soft, right? You can have reconfigurable hardware. You can patch it. So you can actually have intelligence that can actually patch itself and as a result, avoid many failures. Okay, so this was RowHammer. I don't want you to take away the fact that only RowHammer is the memory technology scaling problem. That's not true, actually. Data retention is also a very fundamental technology scaling problem. And today we're refreshing data in memory very frequently, every 32 milliseconds. In fact, this is old paper, sometimes every 16 milliseconds at high temperatures. And it's becoming worse. We're wasting a lot of energy and a lot of performance and a lot of quality of service and predictability on memory refresh, DRAM refresh. But we can actually do much better, basically. If we understand the device, we can get rid of a lot of the refreshes because most of the cells are actually quite strong. And if we understand the software, maybe we don't need refreshes on some data that's not going to live longer, right? So this is, again, an important area where scaling becomes much more difficult in technology as we reduce the cell size because refresh needs to increase significantly, as we mentioned in some of our works like this one. But I think we need to have solutions to this problem so that we get rid of the huge downsides of technology scaling. And sometimes maybe some of these retention errors may be actually slipping into the field as well. And that needs to be analyzed. That's more difficult to analyze than RowHammer, of course. But basically, DRAM refresh is another example where technology scaling is not on our side. And we need to fix the DRAM refresh problem. I'm not going to talk about how we fix it. There are a lot of interesting issues like variable retention time, data pattern dependence, etc. But I will leave you with, I guess, with the flashing of these papers, some of which are very recent. There's one upcoming at Micro, for example, on identifying uncorrectable errors by taking advantage of, or in the presence of error correcting codes inside the chips. But I think this is fascinating. And again, if you're interested in DRAM refresh and data retention and what kind of vulnerabilities it may cause and what kind of issues it causes in terms of technology scaling, again, I would invite you to watch our lectures or feel free to contact us. But refresh is another example where an intelligent controller can identify which cells need to be refreshed at what frequency and refresh them at the frequency that they're supposed to be refreshed at, as opposed to refreshing all of the memory cells at the very high frequency, basically, which is being done today. So an intelligent controller can actually get rid of a lot of the refreshes, as some of the past work shows, more than 75%, even 87% of the refreshes. Okay, so hopefully I've convinced you that we need intelligent controllers due to technology scaling issues, but these are not the only issues. There's an intelligent controller. There are intelligent controllers that are being designed for flash memory, for example. Solid-state drives are quite intelligent. They actually do similar things like what I've been describing so far. I'm not going to talk about them. And industry is also pushing for this as well, even though sometimes they're not successful. This is a paper that I would recommend that was written by Samsung and Intel together, where they basically said that DRAM technology scaling is getting worse. Refresh, variable retention time, write latencies are getting worse. They couldn't talk about RowHammer, unfortunately. But basically, they said by co-architecting controllers and DRAM, meaning having intelligent controllers that understand what's going on, you can improve the technology scaling. Again, I will leave you with this paper. I will give you one last example from the technology scaling perspective before I move on to the systems and architecture perspective, systems and applications perspective. And that's the fact that there are other technologies that are coming up, and the technologies are scaling differently. So DRAM and some other technologies have different upsides and different downsides. And hybrid memory systems can enable us to achieve the upsides of all, both technologies while avoiding the downsides of those technologies, right? By doing hardware, software management and data allocation and movement in an intelligent manner. So this is the idea of hybrid memory systems, and it can be generalized to any technology. As you can see, it could be different types of DRAM, for example. It could be different types of NVM. It could be multiple different types of memory. Of course, complexity becomes an issue over there. But then if you want to scale memory into the future, this is a reasonable direction, basically. If one technology does not scale alone, why not use multiple technologies that have different trade-offs and try to avoid the bad things as much as possible in each technology while exercising the good things in each technology. And I think this is actually very promising, and it's already happening. You can see some references over here. But for this to happen, you again need intelligent controllers that understand the properties of different devices, properties of different data, and do the mapping intelligently between the data and the devices. And these works that I mentioned talk about some of these issues, which I'm not going to go into because I don't have time to go into. Okay, so that was a long-winded discussion of why technology scaling is really pushing us to do something different in memory, meaning designing intelligent memories that really understand these issues and try to avoid the problems, basically. And that requires intelligence. Okay, now let's look at the systems and application side, the higher level side, let's say. On the systems and application side, we essentially have a similar issue. Systems and applications are pushing us to have intelligent memory, meaning data access is a major bottleneck. Clearly, I'm going to show you more results with it. Energy consumption is a key limiter, and data movement energy dominates computation energy. This is especially true for off-chip to on-chip data movement. Let's examine these before we examine these. I'll give you a high-level overview. Basically, the key question in my mind is this: do we want a sustainable world that's beautiful like this, energy efficient, sustainable, or do we want a world where we cannot even breathe? I would argue that we want the best of all worlds, meaning we want high performance as much as possible because we have a lot of problems to solve, and high performance is necessary for that. But at the same time, we want to be extremely energy efficient and extremely sustainable, because otherwise high performance is useless in the long run, right? Or maybe even in the short run, we don't know, if you don't have sustainability, right? We're already having a lot of problems with climate, for example, and computing has become an increasing factor in the effects that we have on climate, as well as in general, because computing power is actually a lot of the system power, entire power that's consumed in the world today. Okay, so what's the problem? Data access is the major performance energy bottleneck in computing systems. We need to go to memory, go to storage to bring the data to the processor and the accelerators. And this clearly causes performance loss. This also causes energy waste, right? Because of our design principles, basically. Our design principle says you're processor-centric, you have to bring the data into the processor. A lot of energy waste, a lot of performance loss, but we try to avoid that performance loss as much as possible, right? What do? We basically design our systems to be extremely complex, meaning we have heavy out-of-order execution mechanisms, heavy prefetching mechanisms, heavy multi-level, many-level cache hierarchies, and huge caches, a lot of interconnect in our systems, and also heavy multi-threading mechanisms, both in hardware and software. And all of these try to alleviate the performance loss of data access. When they work well, they're okay, but usually they don't work perfectly. And much of the time today, they don't even work at all, almost, because some of the workloads are quite random access today. So caching immediately becomes ineffective. Sometimes you have data dependencies, out-of-order execution becomes mostly ineffective, etc. So basically, we add a lot of complexity into our systems to avoid the performance loss of data access. And usually it doesn't work, or many of the time it doesn't work. And as a result, it exacerbates the energy waste, meaning all of these mechanisms are also wasting energy. So basically, we're in a vicious cycle today. Memory access, data access causes energy waste. To alleviate the performance loss, we add even more energy waste on top of the problem. So we need to break this vicious cycle, in my opinion. And the vicious cycle, any vicious cycle, can be broken by really pinpointing the problem at its heart. And the problem is really that processing of data is performed far away from the data. Why don't we fix it fundamentally? Why not enable processing capability right next to or inside where the data is? And that's the idea, basically. Basically, we want to revisit the computing system. We want to get rid of the processor-centric. I mean, get rid of is a strong word, basically. Today's approach is processor-centric, right? Basically, data has to go to the computing unit, whether it be a processor or some type of accelerator or a GPU. Still, data has to move there. And as a result, data storage units have been treated as dumb units, and they're largely unoptimized. We want to change this. In addition to the processor-centric paradigm, we want to have a data-centric paradigm, and we want to decide which one is the best to use for a given application. Okay, so clearly we know that processor-centric design is not that great, right? This is Dick Seitz, who was the chief architect of alpha processors, the flagship processors, and the fastest processors of their time. He basically wrote this one-page article after their team designed the fastest processor of its time. And basically, he said that we designed this alpha processor. It's the fastest of its time. It's capable of finishing 4 instructions every clock cycle. But when we actually benchmark it on this important database workload that we want to do really good at, we are designed for this. But the processor that we designed is finishing 1 instruction every 4.7 cycles, meaning it's operating at almost 1/20th, 5% of its peak bandwidth. And basically, he concludes why? It's because the processor is waiting for data to come back from memory. Data is not in the caches. Data is in memory. It's huge data, and the processor is waiting, stalled. And he basically finishes the article, by saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Only is his emphasis from the paper. And I also recommend reading this paper if you're interested. Fast forward 10 years later, this is my own PhD thesis, where we analyzed together with Intel all of the workloads that they used to design their flagship processors with. We find out the same thing, basically. Most of the time, the processor is waiting for data. Very little fraction of the time it's doing useful work. Basically, it's not stalling. Some of this is wasted, of course, for speculation, etc., that I'm not going to talk about. But if you're interested, you can look at the paper that we have written in 2003 as well. Okay, fast forward 10 years later. If you don't believe me, if you don't believe Dick Seitz, fine. Google, since most people believe Google today, I don't know why, but they do. But basically, Google published this paper in 2015, and they basically showed essentially the same thing. In all of the data center workloads that they execute, the processor is waiting for data most of the time. It's doing useful work only 10 to 20% of the time. And this is a cutting-edge processor. It's not an old processor. It's a cutting-edge processor of its time, as the processors that we had analyzed as well. Okay, I would also recommend reading that paper if you're interested. Basically, we have a problem. We have a processor-centric design mindset and approach and implementation, everything basically. As a result, we have a grossly imbalanced system. Processing is done in only one place, and data moves a lot as a result of this. And this is energy inefficient, low performance, and complex, as I mentioned. And also, a processor becomes overly complex and bloated. That's true for accelerators as well. If you look at a GPU today, it's very complex and bloated. In fact, that's true. That has become true for machine learning accelerators and other accelerators as well, because you need to tolerate the data access from memory. As a result, you need to have complex hierarchies and mechanisms which are energy inefficient, low performance, and complex, especially when they don't work fully or when they don't work at all. So as a result, we're back to the picture that I showed you earlier. Most of the system is dedicated to components that store and move data, yet the system is still bottlenecked by memory and data. Okay, let's take a look at the energy perspective. I'm borrowing this slide from Bill Daly from HighPeak 2015. And these numbers have all changed over time, clearly, but the gist of the conclusion remains. So let's take a look at an arithmetic operation. 64-bit double precision floating point, according to Bill Daly, is 20 picojoules. Energy of a single DRAM write is 16 nanojoules. That's 800x difference. Basically, a memory access consumes between 1 to 2 orders of magnitude the energy of a complex addition. Remove that complex over there, an addition, basically. So given this trade-off, does it really make sense to do just one operation, one simple operation? Does it really make sense to bring 2 operands from memory into the processor, do the simple operation, and then write the data back? Basically, you're doing 3 times 800x, according to these data, to just do a very simple operation. I would argue that in most cases, it doesn't make sense, unless you have very good locality to overcome. I will also mention that this picture is really it's really showing us the success of technology scaling, success of Moore's law, if you will. Basically, what's happening is, if you go back 70 years ago, and if you try to plot the energy of all of these different operations, you will see that a computation is actually about 2 orders of magnitude more expensive than memory access. So over the course of 70 years, we swung 5 orders of magnitude such that the computation became better and memory became worse, or it didn't improve, let's say, as much. So why? This is because of technology scaling. Technology scaling enabled us to build better, faster, smaller, more energy efficient transistors, whereas technology scaling didn't help us much with interconnect and the memory. As a result, memory has become a significant bottleneck, whereas computation has become cheap and easy. And I would also argue that computation is we know what to do when we design computation systems today, but we need to learn what to do when we design memory systems going into the future, let's say. So that's why I think this disparity is quite important. And again, if you don't believe those numbers, there are a lot of numbers that have been published that are similar. And this is why we see more than 60% of the total system energy is spent on data movement in real workloads, according to our analyses. And we're going to get back to this paper as well. So, okay, based on everything that we have said so far, I will argue that we do not want to move data in our system. We want to minimize data movement as much as possible. Of course, maybe I'm exaggerating. Sometimes data movement makes sense, right? As long as it makes sense, as long as you overcome the downsides of it, moving data is okay. But most of the time, we don't want to move data. So basically, we need to have a paradigm shift to enable computation with minimal data movement. Today, we have no option. We have to move the data to operate on it. We want to have options, basically, in the memory hierarchy. We want to be able to compute where it makes sense, where data resides, and data resides in many possible places in the memory hierarchy. We should be able to operate on data wherever data may reside, and basically make the computing architectures more data-centric or memory-centric. And that's the idea of processing near memory or memory-centric computing. So I'm going to talk about main memory for the rest of this talk, but you could apply the principles to any kind of memory structure. Why am I going to talk about main memory? Because main memory is really important and interesting. Clearly, a lot of data gets stored in memory today. Caches are not capable of it today. Storage is too slow today. So main memory is really interesting for that reason today. And today, people have devised applications just to fit main memory. There are in-memory databases that are optimized for main memory. There are in-memory graph processing engines, in-memory machine learning workloads, in-memory media processing. All of these are designed to really fit memory today. So that's why main memory is very interesting today. So what would we like to do? Basically, we have our workloads that are already fitting in our main memory. And if you want to do operations on them, the processor basically asks the main memory, can you execute this function for me on this data set? And the memory says yes, and here are the results. And hopefully that's fast and efficient, because there's no big data movement that happens between memory and the processor. All the data stays here and gets computed on in the memory chip, and only the results get communicated. That's the idea, basically. So, of course, it's easier said than done. There are many questions over here. How do we design the compute-capable memory and the controllers? How do we design the processor chip and the in-memory units? How do we design the software and hardware interfaces to enable this? Both are important. How do we design the system software compilers and languages to take advantage of it and enable this, and enable it more easily for the programmer? And how do we actually design the algorithms and theoretical foundations of computing to be much more data-centric to take advantage of this? I will say that theoretical foundations of computing have been based on processor-centric principles. Basically, if you take a theory of computation course, you know the big O notation or big theta notation. Basically, you're counting operations. Memory never plays a role. We should change that, basically. If you're data-centric, even the theory of computing has to change. Okay, basically, that's why this is an across-the-stack approach. That's why it's fascinating. That's why it's really exciting. That's why there are a lot of research opportunities here, and there will be a lot more research opportunities here going forward as well. Sorry about that. Something happened with my computer. But that's also why this may be difficult to adopt. So we really need to think intelligently to enable adoption of these. Okay, before I delve more into processing in memory, I will mention that we have written this overview article that talks about processing in memory from a modern perspective, that talks about a lot of issues. You can find it on my website as well as on archive. And we cover a lot of topics, as you can see, different types of approaches to processing memory that I'm going to talk about. I'm going to talk about processing using memory and processing near memory today. And we talk about adoption issues as well as research challenges going into the future. So if you're interested in this topic, I would definitely recommend reading it. It may actually give you inspiration on ideas as well as potential research directions, as you can see, are outlined in later chapters. But also they're sprinkled in the paper as well. And I'm happy to get any feedback if you have feedback on this topic. Okay, I think I've been speaking a lot. Are there any questions? Feel free to type them in chat. If not, I'm going to jump into these two, let's say, exciting approaches on how to do processing in memory. Okay, I'll wait for a very short time. Maybe some people are actually waking up. This is a bit early on the west coast of the US, I think. But that's okay. I think I will feel free to put your question to chat. I will start with the two approaches. So processing in memory clearly is an old idea, but these two approaches actually examine it in a new perspective, let's say, because trade-offs have changed. And surprisingly, the processing using memory part has not been explored as much in the past. These two approaches are fundamentally very different. Processing using memory takes advantage of the operational principles of a memory structure to also do computation with minimal cost. Basically, we're going to repurpose or use the operational principles to do computation without adding much logic into memory. So it's very powerful from that perspective, but this also changed the programming model significantly. Processing near memory, on the other hand, is much closer to today's systems. You have memory, you have processor, they're far away from each other. You basically gradually put the processor closer and closer and closer to memory, sometimes inside the memory chip, inside the memory bank. Basically, this is very similar to what we have today, except the processors and the accelerators get closer and closer to memory. They may become inside the memory chip as well. I hear some noise. Is there a question? Okay, I think I still hear the noise. If it goes away, that's good, unless there is a question. Okay, I don't see anything in the chat, I guess. So I'm going to move on. Okay, so keep this in mind. There are these are two fundamentally different directions, and you will see the difference. So as a result of the fact that processing near memory is basically putting the compute units closer and closer and closer and closer and closer to memory, it's easier to program, right? It's you can imagine the programming methodology is going to be very similar, but processing using memory changes the programming model significantly, as we will also see, unless you incorporate it in a simple way, of course, right? Okay, so let's start with the processing using memory part. Basically, this approach takes advantage of the operational principles of memory to perform bulk data movement and computation inside memory. Basically, you can exploit internal connectivity to move data. You can exploit analog computation capability. I'm going to give you examples from DRAM. I'll briefly mention non-volatile memory technologies as well, because I think these are capable of doing different types of operations nicely. And I'm going to start simple. I'm going to talk about data copy initialization, which is really important in many applications today. In fact, Google, in the paper that I mentioned earlier, also showed that in all of their data center workloads, approximately 5% of all of the execution cycles is spent on just two system calls, memmove and memcopy, that do data copy. They also show that whatever I'm going to describe next, the row clone approach, is a very promising approach that can get rid of these cycles. So they actually acknowledge a processing in memory approach or processing inside the DRAM approach that can optimize away this 5%, which is actually quite high if you think about it, just for two function calls, right, in the entire data center. Okay, so how do we do bulk data copy today? This is memory, and we want to copy the source page to this destination page. We have to go through the processor today. Why? Because we're processor-centric. We have to bring the source page byte by byte, destination page byte by byte, do the copy, and write back the data byte by byte into memory. That's a lot of memory accesses for a 4 kilobyte page. And if you imagine a 1 megabyte page or 2 megabyte, 1 gigabyte page, it becomes worse, right? So this is high latency because a lot of memory access, high bandwidth utilization on perhaps the most important resource on our system, the data bus. It causes cache pollution, but you could eliminate that by doing this through the direct memory access engine today. It causes a lot of unwanted data movement. What if the data that you're going to initialize or copy is not going to be used anytime soon? You're moving it to the processor for no reason, essentially. So basically, a 4 kilobyte page copy via the direct memory access engine, not even hurting the hierarchy, let's say, costs about 1,000 nanoseconds and 3.6 microjoules. So can we do better? And the idea is to think data-centric. Basically, if we think data-centric or memory-centric, we would say, do it inside the memory. Move it as little as possible, and you copy the data inside the memory, and you're going to take advantage of the high bandwidth connectivity inside the memory chips. And this is low latency because it's also low latency. You don't need to go through huge interconnects. There's no bandwidth utilization on the data bus to transfer the data. There's no cache pollution, and there's no unwanted data movement. Data needs to be moved to the processor only when the processor really, really needs it. And you can see that I will show you a mechanism that takes us 1,000 nanoseconds to 90 nanoseconds, more than 11x improvement, and 3.6 microjoules to 0.04 microjoules if you optimize it, almost 2 orders of magnitude improvement. Okay, and the idea is very simple. Very quickly, even without going into a lot of details in terms of chart sharing, but we're going to exploit the chart sharing principles of the DRAM. So remember this row, the subarray of DRAM. Basically, if you want to copy one row to another row, and this is the fastest mechanism that I'm going to describe. I'm not going to describe the slower mechanisms where the rows may be in different banks, for example. Ignore that for now. There are other approaches that have been developed after this work that actually made this better. But for this, this is the fastest approach that we know of so far. Basically, the first step is to activate the source row, which brings the data into the sense amplifiers, the row buffer. Now, the data of the source row is nicely stored in the sense amplifiers that are very strong. The next step is to activate the destination row quickly while deactivating the source row. Since the data in the row buffer is still captured, the row buffer drives its contents into the destination row because of the chart sharing principles. Row buffer is very strong. cells are not strong. As a result, row buffer drives its contents into the destination row. So basically, by doing 2 consecutive activates, you use the row buffer as a temporary storage of the source row, and the source row gets copied into the destination row. Negligible hardware cost. In fact, I will show you a paper that shows that you can do it in real systems by modifying the DRAM timing parameters today without making any changes to the DRAM chips. It doesn't always work, of course, because the chip is not designed for this purpose. But the fact that you can actually do it and it works in some systems shows that DRAM is fundamentally capable of doing it. So that's a good proof of concept. Okay, as I mentioned, you can actually get significant performance, latency, and energy improvements by doing this copy inside the DRAM. And there are also interbank and inter-sub-array versions, but these are old. They're new works that are actually improved upon the paper that we wrote in 2013. Okay, if you're interested in more about row clone and its enhancements and processing using DRAM, I'd recommend watching this recent lecture and, of course, reading the row clone paper. But the recent lecture, this was actually I delivered last week in our live class, talks about a lot of issues in processing using DRAM and a lot of mindset issues also to enabling this in real world. Okay, clearly you can do other things on top of this by just exploiting underlying DRAM structure. Faster subarray copy, smaller granularity copies, better interbank copy, and also computation on data, as I will describe. And I'm just going to flash these works so that you have it in your mind. If you're interested, you can take a look at them. Okay, basically, before I go into more computation, I will mention the mindset here. So the mindset is that why not treat memory as an accelerator also? Basically, put capability to memory that it's already very good at, specialized capability. And data moment and data initialization is one. So we are good at designing all of these other accelerators in our system. We have many of them. That's great. They're all compute-centric accelerators. Why not have a data-centric or memory-centric accelerator that's extremely good at what it's doing, and it's not bottlenecked by the memory bus? That's the idea over here. So you can think of memory as a conventional accelerator also. A lot of programming issues arise, again, similar to conventional accelerators, and they have to be solved again, right? Okay, that was maybe cheating. That's copying and initialization, right? Initialization, I didn't even talk about initialization, but initialization is a special case of copy. But if you want computation in DRAM, you can also do it. Basically, we can also support in DRAM and or not and majority functions bitwise. This is bulk bitwise computation, basically. At low cost, again, very little changes to DRAM. By using the fundamental analog computation capability of DRAM that arises due to shard sharing, as well as the sensing. And the idea is if you activate multiple rows concurrently, that performs computation. And this leads to 30 to 60x performance and energy improvement in bulk bitwise operations, as demonstrated by this work that I'm going to briefly mention again. On top of this, new memory technologies enable even more opportunities, in my opinion, because they have a different structure and they can do matrix multiplication, as I will briefly mention. And also, they can operate data with minimal data movement. Fundamentally, DRAM, whenever you actually need to access data, the reads are destructive. You have to move the data at least to the sense amplifiers, right? But that's not true in new memory technologies. In new memory technologies, you can access data without destroying it. As a result, the data movement can be much less. But of course, there are other challenges in new memory technologies. DRAM is here and real, and it exists, and there's a lot of manufacturing capability, and we can actually do even more with DRAM. New memory technologies need to get to that point to be actually really feasible and competitive, let's say, at the latencies DRAM is competitive at. Okay, let me give you the idea. This idea is actually applicable to not just DRAM, but also emerging memory technologies. I'm going to describe it from the perspective of DRAM. But basically, the fundamental primitive is triple row activation. If you activate these 3 rows concurrently, you would get a majority function. So basically, I'm showing 1 bit in each row here. These are the capacitors, these are the access transistors, and this is sense amplifier. Imagine a row being 8 kilobytes. So you can do this operation on 8 kilobytes concurrently. And if you have 1,000 subarrays, you can do this operation concurrently on 1,000 subarrays. So you can operate on 8 million bits at a given time inside DRAM chips, maybe even more if you have a larger DRAM chip, right? But basically, if you connect these transistors, access transistors, at the same time to the bit line, what happens is, in a perfect circuit, if at least 2 of these cells are charged, you get the charge state at the end at the sense amplifier. If at least 2 of them are discharged, you get the discharge state because of the charge sharing principles, right? Which is the principle of operation of DRAM. Basically, in this case, you get the charge state. Basically, because 2 of these cells are basically charged, you get the charge state at the end. And this is a bitwise majority function. And bitwise majority function is a very exciting and very nice function, on top of which you can build many, many computation principles, especially if you add an immersion on top of it. And Donald Knuth, I would recommend reading Donald Knuth's, let's say, a description of the bitwise majority function where he praises it as being one of the most beautiful functions in the world, let's say. Okay, that's bitwise majority. You can use it for computation. You can also take out C and set it to 1. Now you get the OR of A and B. If you set C to 0, you get the AND of A and B. So you can do in DRAM AND and OR as well as majority. Okay, so to be cost effective, we propose it to be done only in a designated part of a subarray inside the DRAM. And those designated rows you need to copy the data from rows A and B, for example. If you want to do bulk operations on A and B, do the ending and store the results in C, you need to first copy, meaning row clone, the data from A and B into these designated rows where you can do triple row activation, and then row clone the reserved 0 row so that you can specify an end, and then you do the triple row activation, and then you row clone the result back into the C row. So this is how it operates, and you can program it actually through the memory controller easily, as we show in the paper. Okay, so and or and majority, those are good functions, but we're missing something that is preventing us from functionally complete. We're missing a NOT, basically. So if we can do a NOT, we can be functionally complete, and we can map essentially any algorithm, with some effort, of course, onto the substrate that can do bulk bitwise execution. And that's essentially what we did in this paper. And I'm not going to go into the details of it, but if you think of DRAM, if you think of the sense amplifier that I showed you, the other side of the sense amplifier actually contains the complement of the data that you sensed, meaning you already have the NOT function because of the cross-coupled inverter, right? Inverters are already there. You don't need to add another inverter to get a NOT. That would be costly. Why not use the same inverter and connect the output of it to another row in the subarray, into a special row that we call the dual contact row? I'm not going to go into the details of it. You can make it work. There are a lot of SPICE simulations and reliable simulations that we did that shows that this works. But basically, this is the key idea. Without actually adding any logic for computation, we actually can put the data back, complemented data back into the array. And that's the idea. Now you actually have a functionally complete bulk bitwise execution system. And it's actually quite powerful. NOT operations are, let's say, 60x more energy efficient compared to DDR3. And you can actually have more complex operations built upon the NOT, AND, and OR. And you can see the average numbers. Those are quite significant, I believe. Okay, so where does this help? Let's take a look at the application side. Now, remember, we were talking about device to applications, and this is one example. We changed some small things. We are exploiting device level principles, and we changed some circuits to enable some other operations. And now we're going to take advantage of it at the application layer. We're going to revise the algorithms to actually get high benefits from the changes that we did at the circuit level so that we can exploit the devices, right? Device level principles. And bulk bitwise operations are quite common in bitmap indices like databases. Some databases are specifically written to maximize bulk bitwise operations so that you can do column scans much faster. Microsoft has written a web search engine that's, again, to maximize bitwise operations. DNA sequence mapping is very much bitwise, as I mentioned earlier. I didn't mention the bitwise portion of it, but the genome analysis is quite bitwise. And encryption algorithms, set operations, I'm not going to go into more detail on many of these, but I'm going to give you some examples. Basically, we ported some of these workloads to our Ambit engine, in simulation, of course, that can do bulk bitwise execution, and we get significant benefits. These are end-to-end results of a query, for example, using bitmap indices, database queries, basically. You get 5.4x to 6.6x performance improvement on end-to-end queries, and performance improvement increases as data set size increases. Another example, if the database is written to maximize bulk bitwise operations, this is an example result for a query where the speed up can reach 12x end-to-end speed up compared to the baseline. And again, speed up increases as the data set size increases. So, okay, there are other results that I'm not going to talk about over here. I will refer you to the first paper that we wrote on the topic, as well as the more complete Ambit paper that talks about this bulk bitwise execution model. And there are more recent papers that we wrote that talk about some research directions as well. Now, let me quickly talk about some programmability issues. How do you actually make this even more general purpose and make it easy for the programmer to actually specify more complex operations, and also make it easy so that there's an end-to-end framework that the compilers can compile into, for example. And that's the idea of the Simdram framework. I'm not going to go into a lot of details over here. This was published at the beginning of the year at the ASPOS conference. But basically, this work is an end-to-end processing using DRAM framework that provides a programming interface, the ISA, instruction set architecture, and the hardware support for efficiently computing complex operations in DRAM. Basically, for example, convolution. If you want to compute convolution, how do you specify it? not just and or not, but more complex operations. Multiplication is another example. Division is another example, right? To provide the ability to implement arbitrary operations as required by the programmer or the system, and while using an in-DRAM substrate that requires minimal change to DRAM architecture, basically the ambit substrate that we talked about. And the framework actually consists of a lot of principles from digital design as well. We actually use some of the principles that were developed at EPFL in Nani Demicheli's group, where you could compile circuits into majority functions. So basically, user provides a desired operation in terms of and or not logic. We basically convert it into majority not logic, which we find to be much more efficient. We then convert it to a sequence of DRAM commands that take advantage of the triple row activation and row clone operations that we discussed earlier. And that becomes stored as a SimDRAM microprogram. And a new SimDRAM micro instruction is added that will call this microprogram when it's executed by the processor. Right? Okay, so when the user actually uses this new SimDRAM instruction, that SimDRAM instruction gets executed according to the microprogram that's stored in the memory controller. And the output is basically incorporated into the program in the end. So basically, you can call this new SimDRAM instruction, bulk bitwise instruction from your program in a seamless manner. And you don't need to deal with how it's implemented because somebody else does it for you. And that somebody else exposes this ISA instructions for you. But you can also add new instructions if your instruction set enables you to do that. So that's a very powerful framework that really takes advantage of this underlying bulk bitwise execution substrate and raises it to a level that's much more programmable. And we find very good results, basically. Evaluated across these workloads, as you can see, we can see significant performance improvements over a CPU as well as a high-end GPU, as well as very high energy efficiency improvements over a CPU as well as a high-end GPU. And I would encourage you to read the paper for more detail. There's a lot more in the paper that I do not have really time for. There's a lot of system integration challenges that are discussed in the paper. And I believe this is a promising processing using memory framework that can ease the adoption of these processing using DRAM architectures, and also improves the performance and efficiency of processing using memory architectures with optimizations that are discussed in the paper. Okay, you can read the paper for more detail. Okay, similarly to this, you can also add security functions by taking advantage of the fundamental device level properties of DRAM. You can, for example, reduce the latencies and create the error patterns that you create lead to signatures in DRAM, which are called physical unclonable functions. I'm not going to go into detail. And also, when you reduce the latencies, those latency reductions can lead to true random numbers if you select the cells that are randomly failing when you reduce the latencies. And this is a very high throughput random number generator that you can do processing using DRAM again. And this is the most recent random number generator that outperforms the previous one by exploiting the quadruple row activation principle. When you activate 4 rows at the same time, for example, this leads to, and you can do it on real DRAM chips, by the way. This is done on real DRAM chips. The results are all on real DRAM chips. You can enable the activation of 4 rows concurrently, and that leads to true random numbers that you generate inside DRAM using, again, fundamental device level operation principles. So I find these fascinating because these works point towards the fact that you can put a security infrastructure on the DRAM side by using DRAM's operational principles. And I think that security infrastructure is extremely important. Somehow my video stopped. I will try to enable it, but I don't know why it's not enabled. Can people see me? Okay.
No, you don't have.
Yeah, I don't know. I don't know why. Yeah, my camera burned out, I guess. Interesting. Yeah, I don't know how to fix this problem, but okay, I guess. Let me stop sharing quickly. Let me see if I can do anything about it. I doubt it, frankly. But my computer is also freezing, so maybe there's a bigger problem than just the camera. Okay. Let me do one test. Okay, stop. Yeah, it's not working. Sorry. I guess we'll continue if that's okay with people. I have another computer here where you can see me from far away if you want. Okay. Okay, let me do something. Okay, I think, yeah, I think I'll continue. This was a good opportunity to also take questions. I don't know if there are questions. Let me see the chat over here in my other computer. Okay, there's a question I think I see. Can the processing using memory techniques affect DRAM reliability? So that's a very good question. So we actually look at the effect of DRAM reliability on these techniques. And they can also, and we find out that certainly if you push the circuits too much, you can affect the DRAM reliability. And these techniques also get affected by DRAM reliability. And those need to be taken into account when you're actually, deciding like what to do, let's say. But these techniques can also put more pressure onto the DRAM by doing more activations, right? So they could actually exacerbate the RowHammer problems. They could actually exacerbate the noise problems potentially. And that needs to be investigated, certainly. So that's a very good question. And I think there needs to be future work that needs to be done to understand the effects much better. Okay. So hopefully you can, people can still hear me, right? I just want to make sure. Okay, good. Because I have some problems with my computer. I don't know why. I apologize for that, but we'll continue. So that's a very good question, basically. How do the processing using memory techniques affect reliability, and how do they get affected by reliability? I think there is more that needs to be done. Okay, now I'm at the end of processing using memory part. We're going to switch to processing near memory part. Before that, I think I will cover this work that used the soft MC infrastructure that we released to show that you could actually do row clone and bulk bitwise operations in a limited manner in commodity DRAM chips. Basically, these folks cleverly took the soft MC infrastructure, reduced the timing parameters to imitate back-to-back activations in row clone, for example, and also to imitate triple row activation by taking advantage of the chips, let's say, latency characteristics. And as a result, in a limited set of DRAM chips, they were able to show that row clone is possible. And they also were able to show that in DRAM and OR are possible. Not as difficult, of course. They couldn't show not because that requires some change to the circuitry, but they showed and OR. So that's a very good proof of concept that DRAM chips are actually capable, based on, as we predicted, based on their fundamental operational principles, to perform bulk bitwise operations. And I think that's certainly good to examine. And I think that also validates some of the discussions that we had earlier. So basically, imagine now, if the chip is actually designed to take advantage of these operations and do them reliably, what else can you do? So there's capability, as we see in these works, as well as our works that I mentioned earlier. What if you actually design these DRAM chips to actually do the computation using their operational principles? And I believe there's a huge opportunity for that. Okay, there's another work that I will mention. This work actually does, again, row clone and bitwise operations and phase change memory in a similar manner. I will show you this picture over here in non-volatile memories. Basically, they can do n row bitwise operations inside non-volatile memory in one step. I'll invite you to read the paper for more details. But basically, this is also quite effective. And I think this is an example of the fact that memories in general are capable, greatly capable of doing bulk data movement and bulk bitwise operations internally with multi-row activation capabilities. And I think that's, again, quite powerful, and we should really be taking advantage of these opportunities going into the future. Okay, now let me quickly cover one more thing. This may also be covered in some other lectures, I'm not sure, but I will also mention the capability of some memories to do in-memory crossbar array operations. So some emerging non-volatile memory technologies have crossbar array structure, and many memories are like that, actually. These crossbar arrays can be used to perform dot product operations using analog computation capability. For example, they can operate on multiple pieces of data using Kirchhoff's laws. And I think this is very powerful as well. And this is a different kind of processing using memory. It's taking advantage of this capability, cross-by array operations, as opposed to multiple row activation operations, interaction operations. And basically, bit line current is a sum of products of the word line voltage times 1 over the cell resistance. And that way, by taking advantage of this fact, you can actually do a dot product operation, right? And computation is in the analog domain inside the crossbar array. But of course, to be able to take advantage of this, you need peripheral circuitry for digital to analog and analog to digital conversion of inputs and outputs in this case. Okay, so let me give a little bit more detail on this one. But basically, if you look at a crossbar array-based memory over here, this is the multiply and accumulate operation, or the dot product operation. You have voltages that are fed to the word lines, and you have data that is stored in the cells. And basically, as you feed the voltages to the word lines, the resulting current at the end is the sum of the voltage times the conductance of the cell. It's V1 G1 plus V2 G2. And that's essentially a dot product operation, right? Basically, it's a vector product. You have this vector that's being fed, and you have the vector of weights, and you basically multiply them. And you can do this in an array basis, and then you can sample the results, and you can convert them from analog to digital at the end. So basically, you can multiply a vector or inputs with a matrix of values, weights in this particular case. And this is powerful, clearly, and this is a demonstration of it. Basically, you have the voltages that are inputs, and you have the resistances that are values, and this is the multiplication result, the current, and that's the result you can guess using Kirchhoff's laws, and you can do this for the entire vector and matrix multiplication, as you can see over in this animation. Okay, so hopefully this is very simple to understand. Of course, there are a lot of issues like reliability, etc., that was pointed out before. All those issues also exist over here. And you need to make sure that it works correctly, regardless. Basically, you need to have digital to analog converters and analog digital conversion. You cannot keep doing everything in the analog domain. You cannot make the size of the array huge, because then you run into signal integrity problems, etc. You also need to add additional shift and add circuitry at the end, so that you can actually aggregate or reduce the output to a single value as you need. So there are other circuitry that you need to add also. But these have been quite popular, clearly, especially in the machine learning domain. Yeah, my computer for some reason slowing down, as I mentioned. Okay, let's hope that it will survive. But basically, in machine learning, you have when you have a convolutional rail, you have an input feature map, and you need to produce an output feature map. And basically, you convolve the input feature map using a filter, and that's what this is showing. The way you can do this in a non-volatile memory is actually by having the filter as your weights inside the matrix, and you can actually stream the input feature map through those filters, do the multiplication, and the result will come out at the end of the bit lines, basically. And this picture actually kind of shows that. I'm not going to go into the details of it, but basically the kernel, which is the weights, essentially, are inside the MVM, and you need to map the data nicely so that the operations are done nicely. You need to carve out the input nicely and stream it into the MVM-based processing in memory array, processing using memory array, such that the input vector gets multiplied with the kernel matrix, and the result is an output matrix in the end. Okay, and this is one way of doing it. Basically, you have NVM capable, or processing using memory capable NVM like this. You need to have memory subarrays, and you need to have processing subarrays, because you need to move data over here. This is one design, clearly. And if you look at the processing subarrays, you're capable of doing matrix vector multiplication over here. But unfortunately, some functions cannot be done this way, some nonlinear functions or some other functions that require different types of multiplication. As a result, they may need to be done in logic, either on the memory chip, or that you have to go back to the memory controller, the CPU, or in a logic layer. So I think this is also fascinating, and it's also quite promising, and there are a lot of other papers related to it that I'm not going to cover right now, but I wanted to mention it since it's also important, and it's also a different way of taking advantage of different technologies to do processing using memory. Okay, and that was processing using memory, essentially. Now let's switch to processing, let's switch gears to processing near memory. And I think near memory is also quite exciting over here, because near memory enables perhaps even more easier to program way of taking advantage of memory-centric computing. And there are multiple opportunities here. One opportunity is taking advantage of a logic layer that's stacked underneath memory layers. And this logic layer, you can build processing elements inside the logic layer, and they have high bandwidth, low latency, reasonably low energy connections to many memory layers on top of them. And other true three-dimensional technologies are under development. There's monolithic 3D, and there's the next project at Stanford, for example, that is an example of future monolithic 3D engines using carbon nanotubes, for example, and resistor memories. And I think these technologies are quite interesting to examine going into the future, because they couple memory and processing together. They're at the epitome of memory-centric computing, if you will. But 3D technologies, even without changing the technology significantly, exist today. They have existed for a while, as you can see from our Ramulator paper here. And we've been looking at this for a while. And there are many interesting questions over here. I'm going to carve out two. One is, what are the performance and energy benefits of using processing near memory as a coarse-grained accelerator by changing the entire system, if you had that luxury, or by performing simple function offloading? This is more adaptable, let's say, at least for in a general purpose manner. And then we're going to look at what is the minimal processing and memory support we can provide, which could also be applicable to processing using memory with minimal changes to system and program. Now let's jump into the first approach. Whenever you have a new technology, it's always good to think about what is the maximal thing I can do with it and what is the minimal thing I can do with it. And we're going to talk about the maximal thing we can do with it at this point, so that we can look at the potentials basically. Okay, if you want to do something maximal with a new technology, then it's good to start with essentially an application. And this is what we started with when we started looking at this in 2012 or so. Graph processing, basically. Graph processing is very important, clearly, in many, many applications. It's especially important in machine learning because a lot of machine learning processing frameworks are actually based on graph processing. And scalable large-scale graph processing is challenging because if you throw cores at the problem, you don't get much performance, but you waste a lot of energy. In fact, a lot of bioinformatics is based on graph processing today as well. Why do you not get performance when you scale the cores? Because you have a lot of random memory access and little amount of computation. Basically, you're heavily memory bottlenecked. So the design we have for accelerating graph processing using near memory processing looks like this, basically. We start with three-dimensional memory plus logic technologies. And inside it, inside the logic layer, we put simple in-order cores. And these cores are connected to each other through some network, and they can communicate with each other. And each core basically controls the memory on top of it. And if you want to update a graph node, you basically need to send a message to the core that houses that graph node. So we don't move the data, we move the functions to operate on the data. And of course, we need to move the intermediate data, right? So basically, data movement is minimized, but what we do is we ship functions to the appropriate data that needs to be operated on. So basically, this is one cube, if you will. And if you want to scale up the system, clearly you can connect these chips together. And you partition your graph nicely on top of these chips so that you minimize inter-chip communication and maximize within, let's say, vault communication. These are called vaults, if you will. So basically, there's some programming that you need to do, programming burden that you need to do to take advantage of the substrate such that you minimize the data movement. But fundamentally, you program it using remote procedure calls. You ship the computation to the data. And fundamentally, this kind of looks like a primitive GPU, basically. It's physically addressed. You basically offload your graph computation on top of it. There's no virtual memory. There's no cache coherence. So in a sense, it's primitive GPU, but over time, it can actually evolve to something maybe even more powerful than GPUs. And also, you can accelerate machine learning on top of this. It's not specific to graph processing, even though we evaluated with graph processing. But of course, you need to have specialized accelerators for machine learning if you really want to take advantage of it, as opposed to simple in-order cores over here. So that's the gist of it, basically. Of course, there's a whole system design. It requires a lot of effort, clearly, to make sure it works and make sure you program it. But it's doable, as we showed, and as later works that came after us also showed. Let me give you the results. Basically, compared to commodity systems that are processor-centric, there's no processor-memory dichotomy, as you can see over here. All of these Tesseract cores have access to 8 terabytes per second bandwidth, whereas the closest, the best previous design at the time is 640 gigabytes per second bandwidth, and it's not memory-centric, as you can see over here, because there's a processor and memory dichotomy, whereas you cannot distinguish between the processor and memory in the high-level view of the system in Tesseract. And this leads to significant performance improvement. Basically, you get 13.8x performance improvement averaged over 5 graph processing algorithms, as you can see. And later works actually showed that by optimizing the system, by doing better scheduling, better data mapping, etc., you can actually increase this to 100x or so. So it's very promising, as you can see, 2 orders of magnitude, with collective effort, of course. And the energy reduction is also commensurate. We showed that you can get about 8x energy reduction average across these workloads. And later works actually improve this by improving the system. And they basically showed that you can go close to 2 orders of magnitude again. So clearly, this is very promising. You can actually customize a system for graph processing and actually take advantage of the very high bandwidth. And I think this is an example of where processing in memory is going into the future also. But of course, this is not easy to adopt, right? You have to change the entire system. Some people may be able to do that, but many people cannot. So how do we actually design a much more general purpose system? And that brings us to simple function offloading. And that brings us to this work that I've been mentioning earlier, the work that we did with Google, where we analyzed the potential of processing in memory for consumer devices. And clearly, consumer devices are very important. They're embedded in our lives, and energy consumption is a first-class concern in our consumer devices. They're going to be even more embedded than these watches, for example. There's going to be even more going into the future. There are going to be many machine learning accelerators, etc. Basically, you can imagine, and the workloads will come for sure, and the devices will come. And we analyze these 4 important workloads, and we basically quantified the energy cost of data moment, and we basically found out what I told you earlier. More than 60% of the entire system energy on these real workloads is spent on data moment. So we wanted to examine the potential solution of moving computation close to data. And clearly, there's a challenge here. We have limited area and energy budgets. So we actually have extensive analyses of this in the paper I'm not going to talk about. But basically, the second insight that enables us to design efficient units is that a significant fraction of the data moment often comes from very simple functions. I'm going to give you examples of this. Basically, you can design lightweight logic to implement these simple functions in memory. You can put them in small, embedded low-power cores, or you can design small fixed function accelerators or reconfigurable accelerators to enable these. And we found out that by having a relatively simple effort, offloading these functions to processing in-memory logic, processing near-memory logic, I should say, reduces energy and improves performance by more than 2x if you're using accelerators. If you're using cores, it's close, but not as efficient as the accelerators. And that's the idea over here. Let me give you an example of some examples of these functions very quickly. Compression is one example that's used heavily in Google Chrome, for example. I'm not going to talk about that. In machine learning, when you're doing machine learning inference, a significant fraction of the energy is spent on data moment to prepare the data, like packing and unpacking operations and quantization operations. And these are actually very simple functions that can be easily implemented with very simple accelerators or clearly with very simple cores on the processing near memory side. And that's essentially what we do over here. Okay. I mean, there's also quantization that I mentioned. Quantization is employed essentially in all networks, if you will. And this is also a simple data conversion operation that requires shift, addition, and multiplication operations. And it's also quite powerful. And again, you can offload it easily to processing near memory. And these are the full functions, well, many functions that we examined in this work. I'm not going to talk about this in more detail, but you can see that these functions all get accelerated significantly by offloading them to either a core or accelerator that's next to the memory in the logic layer. If you actually push the computation to the bank, you can expect even more benefits that we did not do in this work. But as I will show you, some of the processing near memory engines that are implemented today by Samsung, for example, and by UpMem, they're actually pushing computation near the bank because the logic layer is expensive for them clearly at this point, but in the future that may change. And as a result, I believe that this foreshadowing can also foreshadow the benefits that we get from those devices, as I will also show. Okay, that was a more practical approach, let's say. And there are other practical approaches. We also looked at truly distributed GPU processing near memory. We have GPUs near memory, as you can see in the logic layers, and a huge main GPU. And these are smaller GPUs in the logic layer because logic layer is not cheap and it has thermal issues clearly. But we see significant benefits, and we also enable this in a manner that's transparent to the programmer in this work. We look at other examples. We accelerate pointer chasing. We accelerate dependent cache misses. We accelerate prefetching mechanisms. More recently, we've been looking at FPGA-based near-memory processing architectures. We looked at, for example, climate modeling, and this is showed real results that are much better than existing processor-centric systems like IBM Power 9. As I mentioned, we look at specialized accelerators, again, near memory for approximate string matching. We look at accelerators for time series analysis. And more recently, again, we look at neural network models from Google, and we actually design data-centric accelerators to overcome the downsides of existing Google Edge TPU. And I would recommend looking into this paper. There will be a talk about this on Sunday that you can watch online as well. Okay. Basically, this is the key summary of this work. I'm not going to go into details, but basically, the Edge TPU, the Google Edge TPU, suffers a lot because it's a monolithic TPU. It really is designed not cater for different properties of different layers, and it really is monolithic. But whereas we analyze a lot of edge models and from Google. These are proprietary models that unfortunately we cannot open source because they're used in Google. But we find out that there's a huge variability in terms of the characteristics of these layers as well as models. And basically, we design a heterogeneous accelerator framework where two of the accelerators are data-centric so that they can cater for the data demands of some of these layers much better. And you can see that the performance energy improves significantly when you actually design an accelerator that's fit for the data patterns that is seen in cutting-edge neural networks. It also improves cost and area efficiency, as you will see in the paper. I went over this relatively quickly, but I wanted to talk about it because it's actually another example of a data-centric, memory-centric approach that's improving the capabilities of existing machine learning accelerators. Existing machine learning accelerators are very compute-centric, basically. There's a memory bottleneck, but if you actually divide the machine learning accelerator such that some of them are compute-centric and many of them are memory-centric, and schedule the layers accordingly based on their characteristics, you can get significant improvements. Okay, I'm nearing the end over here. I'm going to talk about a few works, and then we're going to hopefully have time for questions also. But if you're interested, we also have a lot of work on FPGA-based near memory acceleration. I think these also show in real systems that you can use FPGAs to accelerate in high bandwidth, using high bandwidth memory to accelerate many interesting applications like genome analysis as well as climate modeling. I don't have time to talk about that. But in the end, all of these point out to the fact that we need to revisit the entire stack. We need to take an approach that's hardware-software cooperative, and we really need to design algorithms to devices. But we also can get there step by step. Now let's talk about that step by step, and that brings us to adoption issues and minimal processing in memory support very quickly. I'm not going to talk about this paper much, but the idea in this paper is that to enable instructions in the ISA such that they encode processing in memory operations. Basically, each operation is a cache coherent virtually addressed post-processing instruction that operates on a single cache block. And basically, it could be like a PIM-AT. Programmer can use this, compiler can use this. And this doesn't change your sequential execution and programming model. There's no change to virtual memory, minimal change to cache coherence, and no need for data mapping because you're restricting the operation to a single memory module. And I think this is exciting because this is easy to adopt processing near memory, or even processing using memory approach potentially if you can actually satisfy these requirements. So dynamically, you can also decide where to execute a PIM-enabled instruction, again, using either software hints or hardware predictors, as we do in this paper. And as a result, you can execute each operation at the location that provides the best performance. And this is an example of where you can do PIM-add, for example, and we have a programming model here. And these are some operations that you can specify in your ISA that are PIM-enabled instructions. You can see that machine learning uses dot product, for example. Hash joins use hash table probing, and there are many, many applications. And I've argued that we need customizable instruction set architectures to take advantage of this sort of processing in memory-enabled instructions as well. Okay, I've already said these. I'm not going to repeat them. But basically, the performance improvements are significant. On 10 emerging data-intensive workloads, graph processing, data analytics, machine learning, and data mining, we get significant performance improvements just by changing the system minimally, let's say. Of course, there are some changes, but they're much more minimal compared to the prior approaches that we discussed. You can see that with large data input set, we get almost 50% average speed up, and the energy reduction is also significant. And you can read the paper for more detail on this. I believe it's a practical approach, and we need to look at these practical approach that can enable you to step by step move into the direction of actually a big revolution, let's say, of data-centric computing. Okay, so I think with this, I've covered two approaches, processing using memory and processing near memory. Let's talk about adoption a little bit. I think adoption is going to be important in both of these approaches. It's going to be even harder with processing using memory, as we discussed earlier. But clearly, there are potential barriers to adoption. I will just mention them: functionality and application and software, ease of programming, interfaces in both hardware and software, compiler support, hardware support, system support for coherence, synchronization, virtual memory, runtime and compilation systems for scheduling, data mapping, and access and sharing control, and infrastructures to assess benefits and feasibility. And I believe all of these are clearly important. I believe all of these can be done, but we really need to change our mindset and put our minds to enable memory-centric computing systems. Now, let me give you a little bit more examples very quickly. We can get there step by step clearly. And I have a lot of discussion in our paper that discusses these issues. But now today is very different from 5 years ago. Basically, today, we have real systems that can implement processing near memory. So these are actually devices, UpMem devices, which we have access to. And these UpMem devices actually have processors inside the bank, in each bank, basically. They call it the DRAM processing units. And you can buy them also if you're interested. And we experimented with this system that has 2,560 DRAM processing units in multiple ranks. And you can read the paper that's on archive over here. And you can also watch the talks. You can see the structure of the processing near memory engine. It's essentially a core. It's essentially a simple core. That's why this is processing near memory, near the bank. And if you're interested, we also released benchmarks to actually run on the system so that we can encourage research in this area. And we look at the performance of these benchmarks. You can find them open source, as you can see. We look at the performance of these benchmarks on the UpMem system. And clearly, we find out that UpMem architecture is fundamentally compute bound because you cannot do a lot of computation inside the memory. But most suitable workloads are memory bound, clearly because of that. And we found out that the most suitable workloads actually do extremely well on this system. They outperform the state-of-the-art CPUs and the state-of-the-art GPUs as well significantly. But they're also not so suitable workloads because they do a lot of computation. In that case, because the cores are not specialized to do that computation, UpMem system does not do very well. So these are the key takeaways that are encoded in the paper. And if you're interested, you can read the paper for more. I don't have time to talk about these key takeaways, and the paper is on archive, as I said. And if you have issues and if you find anything in the workloads or the paper, feel free to contact us. Hopefully the workloads would be useful for enhancing more research in processing in memory going into the future. And you can also find a lot of talks related to this that can initiate you easier. As I said, FPGA-based processing near memory is also real. So this is another real processing near memory-based system. You have FPGAs with high bandwidth memory, and you can do near memory processing in them. And this paper talks about some real results with them. I'm not going to talk about them again. And we actually have an analysis methodology and workloads for enabling near memory processing. Whenever you have near memory processing, one question arises, and the question is that what should you offload and what should you not offload to the cores near memory? And that question is tackled in this paper, where we analyze a lot of applications, and we basically do architecture independent and dependent profiling together to understand what should be offloaded and what should not be offloaded. And we develop a methodology for this that's all completely open source. Again, if you're doing research in this area, or if you're actually are implementing near memory processing systems, you can use them. And these are the applications we study. Basically analyze 345 applications, 77,000 functions, and eventually form the benchmark suite, as well as a categorization of the workloads, and find there are 6 classes of data movement bottlenecks, as you can see over here, and they're tackled using different approaches to the system. Some of them are extremely good for near data processing. Some of them are not good for near data processing. You need a processor-centric approach for them. And again, we release the benchmark suite and toolchain, and we're happy to get any feedback you can find online. And you can also find initiating talks and tutorials related to this, as you can see on the screen. Okay, and that's the paper. Okay, finally, one more promising thing that's happening right now, and that's already happened, is Samsung, a large company, finally decided to put processing in memory capabilities into their chips. And they say that this is for machine learning workloads, but I think they're generalizing it also right now. Basically, this is very similar to UpMem system. You have near bank processing engines that are specialized to do multiply and accumulate operations. And you can read the ISSCC paper from Samsung. There's also an ISCA paper if you're interested related to this. But there's a simple instruction set architecture. It's a very simple processor, especially to do multiply and accumulate operations in neural networks, let's say. And they have a real chip related to it, and you can read more about it. So the takeaway is this is happening, basically. Memory-centric computing is happening. We need to enable it to happen in a more massive scale, in a much better way than it's happening right now, let's say. And this is another recent announcement from Samsung that basically shows that it's not exactly what they did with FIMDRAM, but this is actually a near memory processing engine where they can actually do processing inside the modules over here that they call AXDIM, and they basically accelerate personalized recommendation systems. Okay, that brings me to almost to the end. Basically, if you want to know more about processing in memory and memory-centric computing, there's certainly a lot more lectures that we provide online. There's other tutorials. This is a little bit older version of this tutorial, but this covers some things that I do not cover here because of time limitations. But I will say that we have a huge challenge and opportunity for the future. We want fundamentally energy efficient computing architectures, and that requires us to be data-centric. We want fundamentally high performance computing architectures, and that requires us to be data-centric as well. And because both of them reduce the data moment bottleneck that we have today. And clearly there are challenges, and these are some papers that we have written to overcome the challenges that I didn't get a chance to discuss: coherence, synchronization, virtual memory, data structures, infrastructures, and modeling for PIM. But again, that doesn't change the fact. I think all of these, there needs to be more work to be done to enable these fundamentally energy efficient and high performance architectures. Okay, so that brings me to the end of processing in memory. I do not have time for data-driven, self-optimizing computing architectures, as well as data-aware, expressive computing architectures. I believe they're at least equally important, and they're all part of the They're all synergistic with data-centric computation. But I will invite you to look at this tutorial for more information. And I also will have slides. I will leave these slides. Well, I will send these slides. I would say I want to escape from this. Okay, somehow sharing has stopped. I don't know why. Let me go back to the window. But basically, I will conclude. You can find the information about data-driven and data-aware architectures in the slides or in the other talks. But let me conclude. Okay, I have to, I guess, share again. Somehow, I apologize. I'm having a lot of problems with my video. I don't know why. I enabled my video, but it's still not showing up. So you cannot see me in half of the talk, let's say. But I will conclude regardless. Okay. So basically, this was where we started. Basically, we want to make architectures data-centric, data-aware, and I think we still need to make them that way. We talked a lot about data-centric in this lecture. I believe it's time to design principled system architectures to solve the data handling, in other words, memory and storage problem. We need to design complete systems to be truly balanced, high performance, energy efficient. We want really intelligent systems that are data-centric, data-driven, then data-aware, because data is the major bottleneck today. We cannot continue with the processor-centric approach we've been continuing with for decades. For this, we want to enable computation capability inside and close to memory, and we've discussed that a lot in this lecture. And hopefully I've shown you and convinced you that this can lead to orders of magnitude improvements in performance and energy efficiency, and less quantifiable improvements in terms of reliability, security, and safety, let's say. We can enable new applications and computing platforms like new medical platforms, new genomics platforms. It can enable a better understanding of nature as well, because nature fundamentally is data-centric, in my opinion, and data-driven, and probably data-aware as well, and who knows what else. And hopefully we will reach a much better place in our computing systems where we have much better principles. I do not claim to understand all of the principles that goes on in a system that looks like this. And not necessarily, we don't necessarily want to imitate everything, but we need to revisit the entire stack to enable much better systems. And we need to exploit good principles, some of which I have discussed in this talk. And you can read more, of course, on the slide that I'm not going to talk about now. But I will invite you to read the papers that we have written on the topic if you're interested, and watch the tutorial for the portions that I did not get a chance to cover, and watch the other lectures. At this point, I'll acknowledge all of the people who have funded our research. Please keep funding us. Without that, it's hard to enable this research, as well as these education classes too. And I'll acknowledge my group again. All of their research and our collaborators have contributed to this, and you can read more of their work in these newsletters if you're interested. And everything that I described is available online on my website and also these places. Feel free to contact us if you're using any of the tools, etc. And I'm happy to take more questions right now, since we have, I believe, some time. Thank you. Even though I do not see anyone, I am assuming there are some people on the other end of the Zoom who are listening to us.
Absolutely. Thanks a lot, Onur. This was an amazing lecture.
Oh, thank you, Ariel. I can see you, but you cannot see me. I don't know why.
Actually,
sorry about that.
I can see you most of the time. I mean, it's just now that you become invisible.
Oh, sorry. Yeah, I don't know what happened. My camera doesn't. Now my computer has a mind of its own, as you can see right now. I don't know what happened. What's happening at this point?
Hey, Onur, how are you?
Oh, hi, Andreas. Good to see you also.
You had a new record, 380 slides in 2 hours.
Well, I don't think I covered everything.
I know, I'm just kidding.
Sure.
Yeah, but we should take questions. We have 5 minutes left or so, right?
Yeah, I'm happy to take any questions, either right now or after the talk also, if they email any questions. I hope I did not RowHammer people. I know
that's why we are asking questions, because we are in error.
Yeah, any questions? Anyone? I think I see something in chat. Okay. Yeah, I think people can read it. It's not a question, but Emirjan wants to thank me, and he finds it inspirational. Thank you for the kind words. I'm glad that the lecture is useful, and the other lectures that you have seen are useful also. And it's great that an undergraduate student is also attending this and wants to pursue an academic career. That's wonderful to hear. That's part of the reason why we have these classes, I think, why Andreas and Avial and Akash are organizing this as well.
Yeah, we hope everybody can benefit from it. Right? We're trying to reach a non-traditional academic conference audience, I guess, with this.
Yeah, wonderful. Yeah, that's one of the reasons why I like also giving lectures in venues like this. You usually reach a bigger audience who wants to get into research on these topics, for example.
Well, thank you, Onur.
Okay, yeah, thank you.
If there are no more questions, you can drop off anytime, right? We have the other class starting in like 2 minutes.
Okay, sure.
There's something in the chat.
Okay.
More thanks, I guess.
Okay, yeah, I don't see a question, but that's another thank you note, I think.
Yeah.
I guess looks like that's another undergraduate student, Daniel. And okay,
Yeah.
cool, wonderful.
And maybe you can also be available. We have the Gather Town space to hang out and mingle, right?
Okay.
You can maybe help if anybody wants to meet there, right? Potentially, but we also have the other class starting now. And like,
okay, is that Gather Town space available right now, or is it some other time?
Yes, it is.
Okay,
it is. Yes.
Okay, I'll try to hop on. I need to fix my camera, I think, for that to be a bit more meaningful.
we have a networking session at the end of the second class in Gather Town. Maybe you can be there. If you have problems, let me know.
Okay, sure. I'll let you know. Okay, thanks.
One more question, I guess, in this chat. Can the marginal value setting be an update for the accuracy? I don't know whether that makes sense to you.
Yeah, I'm not sure if I understood the question. I mean, the writing operation. Yeah, can you elaborate? I'm not sure what that means.
Yeah. Sorry, can you hear me?
Yes, I can hear you now.
Okay. I do research in the resistive memory unit, and I found actually there's accuracy swing when we use high frequency writing and rewriting operation. But I'm just wondering if we get enough margin value between the reading and writing operation. So the adjacent accuracy effects you just mentioned will be much safer than we set a not much a closer reading and writing voltage.
I see. Yeah, I mean, I think it really depends on the technology and how much margin is there for the read-write operations in the technology, right? For example, in DRAM, there's a lot of margin in terms of latency for DRAM reads and writes, but that may not be true for the resistive memory technologies. It depends on what you're going to use for and what kind of latencies you specify. So I think it's hard to give an exact answer without knowing the technology and the parameters and how it's going to be used. Does that make sense?
Yeah, because I just noticed that you just mentioned that there are 3 years all the memories devices will be affected, and I believe that that covers all the technologies. Yeah.
Affected in terms of like errors like RowHammer, read disturbance, some sort of errors, right?
Yeah.
Yeah. I mean, certainly. I think any memory technology that scales down to small enough technology nodes will have noise and reliability issues, read disturbance, write disturbance, retention. Yeah, all of those issues will be affected. So certainly these margins will get more dangerous to exploit, let's say, as technology scales down.
Okay, so that means that means there's no certain way to give a clear barrier between the reading and writing to keep a high accuracy in this kind of memory devices.
Yeah, I'm not exactly sure because I have to see what you're exactly working on. But if you, for example, if you don't rely on margins too much, and if you can build a sensing circuitry and analog to digital conversion circuitry to be robust, then I think it's certainly possible to still do computation. But of course, you need to be careful, right? Analog computation is always vulnerable to noise, and you need to keep the noise margins in check. If your arrays are huge, for example, the probability that you're going to get an error is going to be higher. If you keep your arrays small and partition and exploit parallelism across the arrays, then the probability of you getting an error due to the noise is going to be lower, right? So I think in the end, it really depends on how you design the circuitry and the sensing components and the digital to analog and analog to digital conversion components. So if you put higher cost to the device, you can make it more robust, in my opinion.